Hello ATS 113 students, Dr. Shraggy here, and this is the first lecture in ATS 113, also known as Environmental Sciences 113, and I decided today to record the lecture outside. It's just a really pretty day. I apologize for the birds and the sounds of the neighbors mowing the lawn and stuff like that, but I think that we're all going to enjoy having a class outside, even if it is sort of a virtual class outside today. On this first day of the lecture, we do the kinds of things that frankly all basic science, basic anything, philosophy, whatever type classes do. We kind of define the problem and so on that we're going to be talking about in this semester of this course. And though it's a little bit cheesy, but we're going to be talking today about a few basic ideas. We're just going to give a very brief overview of the atmosphere in general. We're going to talk about things like what is meteorology versus what is atmospheric sciences and so on. And then we're going to talk about what the atmosphere is made of, what kind of gases go into the atmosphere, where do they come from, where do they go, how long do they last in the atmosphere, and so on. And then finally we're going to have a section that's going to be about the origin of the atmosphere. Why does Earth have an atmosphere at all? I mean, the moon doesn't have one. How did it come to pass that the Earth had an atmosphere? So we're going to start then with this sort of overview of the Earth's atmosphere. And as much as so much of our lives depends on the atmosphere, it's actually kind of amazing how small the atmosphere is compared to the big ball of rock that we are on. Some printings of the textbook in the past have gotten all bogged down in this idea that the big ball of rock that we live on is called the lithosphere. Don't worry about that word. In contrast to the atmosphere, which is the big ball shape of gas that we breathe and need for life. And that ball of gas, that atmosphere that covers the Earth, is actually really small. In fact, your textbook likes to point out that there's sort of an analogy here. If the size of the atmosphere is to the size of the Earth, as the skin of an apple is to the size of an apple. I mean, it's just this very thin little shell of gases perched on top of a very large ball of rock. In the same way, there's just a very thin apple peel on top of a lot of apple that you would eat or whatever. There is no actual top, though, to the atmosphere. It might give you that analogy might give you the sense that there's sort of a top, how high up you can go in the atmosphere, but actually there is no well-defined top. About 90% of the mass of the Earth's atmosphere resides below about 16 kilometers, and your textbook throws out some of these numbers like this, and different printings have slightly different numbers, but certainly once you get to, say, 100 kilometers up, virtually 100% of the mass of the Earth's atmosphere is below that. Now, when we do the vertical structure of the atmosphere lecture, which is coming up shortly, you'll see that there are, in fact, parts of the atmosphere. There are gases that continue up higher than 100 kilometers, but 100 kilometers is a good round number if you wanted to say just how high up does the atmosphere extend. Beyond about 100 kilometers up, for all intents and purposes, you are in space. Now again, because it's the first day of a class, one of the things that you always do on the first day of class is sort of define your terms. What is philosophy? What is theology? In that sense here, we're going to ask, well, what is meteorology and what is atmospheric sciences? I mean, we're in a class called that. We better make sure we understand what the difference is and so on. Well, I got out of your textbook this definition. It said that meteorology is the study of the atmosphere and the processes that cause weather. Now, I was a little surprised when I saw that definition. I've been doing this for a long time, and I gotta say, that did not sound like meteorology to me. In fact, if I were going to be, telling you a definition here, and I am, and if I looked at other textbooks, which I did, I'd say we could cross out that word meteorology. That doesn't sound right to me. I would say atmospheric sciences are the study of the atmosphere and the processes that cause weather. You probably have noticed that this course is called Atmospheric Sciences 113, not Meteorology 113. And in fact, if I were going to say, if I were even going to make a little bit more adjustment to that definition, I'd actually say that I'd add the words "and climate" at the bottom there. I'd say that atmospheric sciences are the study of the atmosphere and the processes that cause weather and climate. That's what we're going to be doing all this semester long. We're going to be learning about the processes that cause weather and climate. What causes weather to happen, what causes the climate to be what it is, and so on. Just to be clear here, weather is distinct from climate in that weather is sort of a short time scale phenomenon, like what's happening right now, which is very different from climate, which is sort of the long-term average. What is a typical day at this time of year here versus what is today's afternoon high going to be? Weather is the short term, what's going on right now. Climate is the long term, usually over a period of like 30 years. What was the on such a beautiful spring day, what is the typical high temperature? Or what is the typical amount of precipitation to be expecting or whatever? So if that's going to be our definition of atmospheric sciences, that does lead us to wonder what we're going to do about this word meteorology. I mean, our textbook is clearly not going to give us a good answer about that, because our textbook thought that meteorology was the study of the atmosphere and the processes that control weather and climate. Meteorology, I would say, and again, having looked at other textbooks, a better definition of meteorology is to say that meteorology is the art and the science of predicting weather. It's more expressly about what is the high temperature going to be today? What are the chances of rain here? What direction is the wind going to be today? And so on. Some of what we do in this class is going to be meteorology. In fact, we have a whole day towards the end of the semester where we kind of are putting things together to talk about how forecasts are made, for example, or how we're going to be knowing whether thunderstorms develop and so on. But that is not what most of this course is about. Most of this course is about the processes. What controls the temperatures? What controls the amount of rain we get? What determines the climate of our region, etc. This is an atmospheric science class, not necessarily a meteorology class. That's why it's listed as Atmospheric Sciences 113. Okay, moving on to start talking about our second section of the lecture today, which is about the constituents of the Earth's atmosphere. Before we get any farther in that, let me just make sure that you understand what this word constituents means. This is the word constituents in terms of like ingredients, what it takes to make up, in this case, the atmosphere. And, you know, I mean, again, it's the first day of a class, we have to have our kind of cheesy definitions here, and one of the definitions that we need to have is, what is air? And I like this definition that came from the textbook about air is a mixture of gases and aerosols. Let's forget about this word aerosols for a minute and focus on this word mixture. I mean, I think you guys know what gases are, right? You got to this point in your education, you know what gases are. Mixture, as in they've been stirred together and they are combined, but they're still separate. They're separate materials. Think about Kool-Aid. When you make Kool-Aid, you pour water together with sugar and the flavoring packet that comes when you make Kool-Aid, and store it together. It is a mixture. But I mean, it's still made of water molecules and sugar molecules and whatever the molecules are that are in the Kool-Aid packet. They're not changed, they're just cut together. And that's the same with the atmosphere as well. We're going to find out that it is a mixture of gases, things like nitrogen and oxygen and carbon dioxide and water vapor. And they're mixed together, but they're still separate. I mean, there's still oxygen molecules and carbon dioxide molecules and so on. We'll come back to this idea about aerosols in a little bit, because that's a whole different thing. But think about all these gases that are out here in the air with us. There's gases like nitrogen and oxygen and water vapor and carbon dioxide. All these gases got here somehow. Somehow or other, these oxygen molecules got into the atmosphere, and the process by which they are added to the atmosphere is called a source. That's in contrast to a process that removes them from the atmosphere that's called a sink. Now, before we get any farther, let me just give you a little, let me let you in on a little secret, if you will. Behind the scenes on a course like this, we actually have a set of goals as to what the students are going to learn over the course of the semester. And then over the course of the semester, there are special questions on the test that measure, did you actually learn that? No one tells us we are or are not supposed to tell you about those goals and so on, so I'm going to tell you about one of them right now. One of the important goals in this course is understanding about sources and sinks. Processes that add something to the atmosphere, a source, or a process that removes something from the atmosphere, called a sink. Now, we're going to be talking about sources and sinks today in terms of like gases. What is a source of oxygen? What is a source of nitrogen? What is a sink of carbon dioxide? But we'll actually see these terms over and over again over the course of the semester. They will be on the test. They will be on the homework. You are being measured in terms of how well you are being assessed as to how well you understand these terms. So let's make sure we get them. Let me focus first of all. Let's look at that word source. All right, if we were talking about like water vapor, what is it? Water vapor is a gas in the air around us. We would probably use the word humidity to describe it. What is a source of humidity in the atmosphere or water vapor in the atmosphere? Well, the source of it, the process that adds that gas to the atmosphere, would be evaporation. If there were water on the ground right now, as it is added to the atmosphere, that would be a source of water vapor to the atmosphere by the process of evaporation. Probably better would be the use of the word evapotranspiration. Evapotranspiration includes the effects of how plant leaves add water vapor to the atmosphere as water vapor escapes through the leaves of the plant. In contrast, a sink for water vapor. If we were talking about how we remove water vapor from the Earth's atmosphere, I'd go with condensation, where we are changing water vapor back into liquid water droplets. That could be like the formation of dew overnight, as you condense water vapor in the atmosphere out into little drops of water on the grass. Or that could be the formation of a cloud. Clouds are made up, as we're going to learn in this class, of tiny little droplets of water. They're liquid. Water vapor is condensed into cloud droplets in the cloud. And so, okay, we've got this idea of a process that could add water vapor to the atmosphere, or processes that could remove it, a source of water vapor, or a sink of water vapor. Watch for those ideas not only through this lecture, but really all semester, okay? I guarantee that kind of stuff is on the test. Now, each of these gases that we have up in the atmosphere is going to have two important properties associated with it that describe how that gas gets in the atmosphere and stays in there. There's going to be two key terms here. One of those terms is the reservoir. The reservoir, when you think about reservoir in the context of like a lake, right? A lake, when the Corps of Engineers builds a reservoir, it's an artificial lake that stores water. The word reservoir means like as in it's how much is being held. A good dictionary definition of reservoir in this context then would be the amount of the gas that's currently in the atmosphere. Now this could be measured in terms like kilograms. How many kilograms of oxygen are in the atmosphere? It's going to be a big number. Or it could be like a density, or it could be parts per million or something like that. But it's just a way of measuring. When we talk about the reservoir of a gas, then we're talking about like how much of it is there out there in the atmosphere. You know, typically expressed in something like kilograms or something like that. Then, because we have this idea of reservoir, we also have ideas like sources and sinks. Gases get added into the atmosphere, they're part of the reservoir of that gas, and then they eventually are removed from the atmosphere by a sink process. How long were they up there in the atmosphere? The residence time. The average amount of time, or a typical amount of time, a given molecule of that gas will actually spend up there in the atmosphere. That will have units of time. Something like seconds or years or something like that. So for example, for oxygen, a source of oxygen for the Earth's atmosphere is photosynthesis. The plants are putting oxygen into the atmosphere. The oxygen enters the atmosphere and becomes, you know, a part of the reservoir of that gas in the atmosphere. But at some point, we breathe it in and take it out of the atmosphere as it enters our bloodstream through the process of respiration. Respiration is a sink of oxygen in the Earth's atmosphere, and therefore there was a certain amount of time that a typical oxygen molecule got to be loose up there in the Earth's atmosphere. That's its residence time. There's actually going to be a formula for computing this. Some gases are going to have very long residence times, like millions of years, and some gases are going to have relatively short residence times, like days, okay? And some will have it someplace in between. This is something that we need to be able to compute about the atmosphere. And so we're going to use this little formula where the residence time of a gas is just the reservoir of the gas, which is going to have units of something like kilograms, divided by the input rate, how fast we're adding that gas to the atmosphere. So like the input rate might be something like kilograms per second. Okay, how many kilograms of oxygen are being added to the atmosphere every second by photosynthesis in plants? And you're dividing that number into the reservoir. How many kilograms of oxygen are there out there? So this is going to have, you know, the numerator is going to have units of like kilograms, the denominator is going to have units of like kilograms per second, and if you work out those units, it works out to, in this case, to be seconds. Okay. Once you have them in units like seconds or whatever, you could convert them to years or whatever it needs to be if you have like a giant number of seconds. So let's start thinking then about these individual gases. Let's take some examples of some individual gases and think out what would their residence time be. For example, let's consider the example of water vapor. Now, the reservoir of water vapor is actually relatively small. We're going to see in a little bit that, you know, only under the very most humid conditions is the amount of water vapor in the Earth's atmosphere even as much as like 1% of the air. Okay? Compared to other gases in the Earth's atmosphere, there really isn't that much water vapor. So the reservoir of water vapor is pretty small. So the numerator of our equation there for residence time, the numerator, the top, is the smallest number. I mean, don't get me wrong, it's still going to be millions and millions of tons of water vapor, but it is small compared to when we get to like nitrogen or something like that. Now, the input rate, on the other hand, is relatively fast. 70% of the Earth's surface is covered by the oceans. All those places have evaporation going on all the time. Most of the rest of the surface of the Earth is covered with plants. They're continually pumping water vapor into the Earth's atmosphere by the process of evapotranspiration. There's actually a lot of processes that are adding water vapor to the Earth's atmosphere. The input rate is pretty fast. So the denominator, the bottom of the fraction there, is going to be a pretty big number. So you have a relatively small number in the numerator divided by a relatively big number, you end up with a relatively short residence time for water vapor. In fact, if you work through the math, it works out to about 10 days. In other words, someplace out over the ocean, a water vapor molecule evaporates off the ocean and is now part of the atmosphere. On average, it will take about 10 days before that condenses out and is once again a liquid that falls out in the form of rain. All these plants around me right now are evapotranspirating water. Their roots are pulling water out of the soil and putting it up into the atmosphere through the process of evapotranspiration. Those water vapor molecules will on average be up there in the atmosphere for about 10 days. That's a relatively short residence time as gases go. On the other hand, let's consider the example of oxygen. Now, oxygen is another gas in the Earth's atmosphere. This gas has a relatively large reservoir. We're going to see in a little bit that about 21% of the Earth's atmosphere is oxygen. That's a lot of tons. I mean, that's billions and billions of tons of oxygen out there in the Earth's atmosphere. Now, the input, so the numerator of our fraction there, when we're doing reservoir divided by input rate, the numerator is fairly big, but the input rate is pretty big too. The rate at which oxygen is being added to the Earth's atmosphere by photosynthesis in plants is pretty fast. So the denominator of that fraction is pretty big too. So you have a big number in the numerator, but a biggish number in the denominator as well. When you actually work out the math, you end up with a fairly, let's say, moderate residence time. A typical estimate is somewhere around 500 years. So right now, these plants around me are putting oxygen into the atmosphere by the process of photosynthesis. And as they do that, those oxygen molecules are liberated and they're flying around in the Earth's atmosphere. They're a constituent of the Earth's atmosphere. At some point, they'll be breathed in. Now, actually, every time you breathe in, the vast majority of the oxygen molecules actually get breathed right back out. Your lungs are not that efficient at moving oxygen across into your bloodstream. But at some point, you will breathe those oxygen molecules in, and they will be taken out of the atmosphere and put into your bloodstream. They'll have been removed from the atmosphere by the process of respiration. That is, the sink of the oxygen will have been respiration. And the average amount of time that those oxygen molecules will have been bumping around in the Earth's atmosphere is about 500 years. That's a lot longer than 10 days. Now for one more example, let's do nitrogen. Okay, nitrogen, N2, two nitrogen atoms hooked together to make a nitrogen molecule. Nitrogen is by far the biggest constituent of the Earth's atmosphere. It's like 78% of the Earth's atmosphere. The reservoir of nitrogen is huge. On the other hand, the input rate of nitrogen to the Earth's atmosphere is really, really slow. The processes that add nitrogen to the Earth's atmosphere, the sources of nitrogen in the Earth's atmosphere, are not that fast. They're like processes that bacteria engage in soil. Okay? The input rate is a very small number. So you have a huge number in the numerator for residence time. You have a small number down there in the denominator for the input rate. You end up with a very, very long residence time. If you actually work through the math, you end up with 42 million years. In other words, right now, maybe in the soil around me, there's some nitrogen-fixing bacteria that are doing some things, and they are adding or removing nitrogen from the Earth's atmosphere. Those nitrogen molecules are going to be bouncing around in the Earth's atmosphere for about 42 million years before the sink of nitrogen removes them. And the sink of nitrogen is also certain processes that bacteria do in the soil. 42 million years is a lot longer than 500 years for oxygen, and it's a lot longer than 10 days for water vapor. In fact, this gives us an idea that actually, based on the residence time, we should be able to sort the components of the atmosphere, or the constituents of the atmosphere, out into two piles. We're going to say that depending on their residence time, we're going to call them either constant constituents of the Earth's atmosphere or we're going to call them variable constituents of the Earth's atmosphere. Let's start with the constant constituents. Constant constituents are gases that are in the Earth's atmosphere that occur at about the same concentration anywhere you go in the atmosphere, whether from one location to another, or one height to another, or from one time to another. Good examples of the constant constituents that we've seen so far have been nitrogen and oxygen. Oxygen is about 21% of the Earth's atmosphere. It's 21% of the Earth's atmosphere right here where I'm standing. It's 21% of the Earth's atmosphere where you're standing. If I went up in a hot air balloon, it's 21% of the Earth's atmosphere up there. And don't get me wrong, the total amount of air up there is going to be less. There might not be all that much oxygen up there, but it's because there isn't that much air. Okay? Everywhere we go, it's about 21%. Why? Because 500 years is a really long time. Once that oxygen is added to the Earth's atmosphere by, say, a forest, for 500 years the winds and the storms and the circulation of the Earth's atmosphere stirs the Earth's atmosphere. There isn't more oxygen over here by this tree than there is over by that field, than there is over that parking space over there, because over the course of time it all gets stirred together. Imagine, for example, if you were making a cake. Okay? If you first pour all the ingredients into the big bowl. You've got cake mix and eggs and milk or whatever's all in cake, I have no idea. If you kind of just stirred it a little bit, there'd still be places in that bowl where there's more flour and less egg, and over here there's more egg and less flour, and it wouldn't be very well mixed. You could go from one place to another in the bowl, and you'd have different amounts of each of the constituents of the cake mix. On the other hand, if I stirred that cake mix for 500 years, there would be exactly the same amount of egg as cake mix, as oil, as water, whatever is all in cake, in every single spot. And that's the way our atmosphere works too. 500 years is a really long time. By that time, over that period of time, all the oxygen is all just evenly mixed throughout the Earth's atmosphere. Same with nitrogen. Nitrogen is going to be a constant constituent too. 42 million years? 42 million years of mixing. It isn't like the air farther away from the background. I mean, if the soil is where the nitrogen comes from the bacteria that are in there, it isn't like there's going to be more nitrogen near the ground. For 42 million years, that's all being stirred together. In contrast, we're going to have the variable constituents. These are going to be gases that have relatively short periods of time that they last in the Earth's atmosphere. There'll be more of those gases near their source. There'll be less of those gases near their sink, because they haven't had time to be evenly mixed. Water vapor is going to be our greatest example of this, because, like, you know, there's a wide range of where water vapor can come from on the Earth's atmosphere. Over the ocean, there's huge sources of water vapor. We can be adding water vapor all the time. Over deserts, there's almost no water vapor being added. And 10 days is not enough time for the winds to stir the water vapor, to spread the water vapor evenly over the whole planet. Long before the water vapor would be stirred evenly where every place on the Earth's atmosphere had the same amount of water vapor, the water vapor will have condensed out in the form of clouds and precipitation or dew or something like that. We'll be learning more about that in the lectures to come. But this idea that we're going to be breaking the list of gases up in the atmosphere up into constant constituents, the ones that it doesn't matter where you go, they're the same amount, and variable constituents, which you have to measure because there could be a very different amount in one place versus another, will be interesting. Let's focus first on the constant constituents. We would say that the constant constituents of the Earth's atmosphere, here's a power vocabulary word for you, we would say that they're in steady state. When we say that they're in steady state, what we mean is the input rate of that gas is about the same as the output rate. We're not getting more and more oxygen all the time in the Earth's atmosphere. The addition of oxygen to the Earth's atmosphere by photosynthesis is almost exactly the same as the removal of oxygen by the sink process, which is respiration. And so they're in basically steady state. The amount of oxygen doesn't change from time to time. 500 years is more than enough time for it to be well mixed through the Earth's atmosphere. It doesn't change from place to place, etc. Usually there's actually some kind of equilibrium going on between the sources and sinks, but we won't get too bogged down in that. You might notice there's a paragraph or two about that in your book. If I made a little pie graph here to show you your constant constituents of the Earth's atmosphere, what you'd immediately notice is nitrogen just runs the whole show. 78% of the Earth's atmosphere is nitrogen. 21% is oxygen. 78 plus 21 is 99%. 99% of the Earth's atmosphere is just nitrogen and oxygen. Yeah, absolutely. And another gas, argon, it's only 0.9%. So now let's see, we got 99.9% of the Earth's atmosphere. We've only looked at 3 gases. Yep, those 3 gases are pretty much the whole show. We know nitrogen is actually not that interesting in terms of what it can do. Nitrogen is very inert. It kind of just takes up space in the atmosphere. Oxygen, of course, is very interesting in terms of its role for life and so on. Argon, again, isn't very reactive, and neither is our 4th gas on there, neon. Neon being so small. By the way, that is the order. Those are the 4 biggest gases in the Earth's atmosphere in terms of how much of the Earth's atmosphere they occupy. You don't have to know these numbers, by the way, although the first 2 might be kind of handy to keep, have a broad sense that about 3/4 of the Earth's atmosphere is nitrogen and about 1/4 is oxygen. It's more likely that you'd have to do something like put these constituents of the Earth's atmosphere in order from most abundant to least abundant or something like that. In contrast, the variable constituents of the Earth's atmosphere have concentrations that vary from place to place or from height to height or from time to time. You need to measure them. Because they're not going, I don't need to measure how much oxygen's out there. When a meteorologist goes out to take a weather observation, they don't measure how much oxygen there is. We know it's going to be 21%. Okay? But we do have to measure the amount of water vapor in the Earth's atmosphere, the humidity, because it's going to vary a great deal. So, for example, water vapor. Water vapor can range from basically 0% of the Earth's atmosphere under very dry conditions to, okay, your textbook says 4%. That would be ridiculously humid. I mean, I suppose it's physically possible. A good average worldwide would be something like 1/4%. I mean, not very much of the Earth's atmosphere is water vapor at any given time. Hey, I like that little picture, by the way. I included on there. That is a special type of satellite image called a water vapor satellite image. When you think of satellite pictures, you're thinking of there's cameras on the satellite and looking down and it shows you things you can see. There are other types of instruments on a satellite as well that can measure other things, and one of the things they can measure is the humidity of the air. And so what you're basically seeing there is a satellite picture that showed the humidity of the Earth's atmosphere at a particular day, with white being more humid and browns and blacks, or whatever the color turns out to be, being less humid. And you can see that there are places that are very humid and there are places that are very dry, and you need to measure the amount of water vapor in the Earth's atmosphere in order to know how much it's going to be. Another variable constituent of the Earth's atmosphere is carbon dioxide, or CO2. Recently, the carbon dioxide concentrations in the Earth's atmosphere hit 400 parts per million. Part of the story is that carbon dioxide is increasing with respect to time. If we zoom in here, you can see how there's kind of a trend. These are carbon dioxide measurements that come from a particular weather station that's famous in Hawaii, far from any sources of pollution or anything like that. You can see how there's an upward trend over the last, few decades. I don't know how long the particular graph that I have here extends, but you can see that there's this upward trend in the amount of carbon dioxide in the Earth's atmosphere, and that's due to the burning of fossil fuels. Gasoline, diesel, coal, things like that, natural gas, etc. Adding those gases to the Earth's atmosphere has increased carbon dioxide from a pre-industrial level of about 280 parts per million roughly to now we have crossed 400 parts per million. So we haven't quite yet doubled the amount of carbon dioxide in the Earth's atmosphere, but we're getting there. By the way, you can see how there's also kind of a little wiggle to the line. There's sort of an annual cycle to the amount of carbon dioxide in the Earth's atmosphere. That has to do with the fact that carbon dioxide's removed by plants, right? Plants are the sink of carbon dioxide. They remove carbon dioxide as part of the process of photosynthesis. The source of carbon dioxide, of course, being respiration. Well, there are different amounts of plants in the northern hemisphere and the southern hemisphere. The northern hemisphere has much more land than the southern hemisphere does, and a lot of the land in the southern hemisphere is Antarctica, and Antarctica doesn't have any plants. So in northern hemisphere summer, when plants are active, they're removing a lot of carbon dioxide from the Earth's atmosphere, and the total amount of carbon dioxide in the Earth's atmosphere goes down. In the winter, in the northern hemisphere winter, when plants are dormant in the northern hemisphere, they're not removing carbon dioxide from the Earth's atmosphere, and the total amount of carbon dioxide goes up for a while. So there's this really neat annual cycle to the amount of carbon dioxide in the Earth's atmosphere, just due to the fact that there's so many more plants in the northern hemisphere than the southern hemisphere. But then none of that is enough to counteract the fact that we are rapidly adding carbon dioxide to the Earth's atmosphere, and we'll be learning this semester about the consequences of that. Another good example of a variable constituent in the Earth's atmosphere is ozone. Ozone is a gas. I know sometimes you hear about the ozone layer or the ozone hole. That can be confusing because you don't get the idea from that ozone is actually a gas. I mean, we could fill a balloon with ozone, or we could fill a jar with ozone or something like that. It's a nasty, toxic gas, but it's also necessary for life on Earth, as you're going to see in a later lecture. And it's a variable constituent. You have to measure the amount of ozone there is in a given location. That's how we found the ozone hole. Again, we're going to have a whole lecture about the ozone hole and so on coming up. But the ozone hole is this area over the southern hemisphere where the ozone concentrations have basically fallen to zero. On this other diagram here, I want to show you, this is the profile of the amount of ozone at different heights in the Earth's atmosphere. And what I want you to notice is, boy, there's that big spike in the amount of ozone, about 25 kilometers above the Earth's surface. That's the ozone layer. It's a place in the atmosphere where there's a lot of ozone. We'll learn more about why and what it's good for and all that kind of stuff. But see, again, here we had to actually measure. You can see how at different heights there was a very different amount of ozone at different heights above the ground. We'll learn about the sources and sinks of ozone. Not the next lecture, I don't think. Well, maybe it's the next lecture. It's either the next one or the one after that. Another variable constituent of the Earth's atmosphere is methane. Methane is natural gas. It is what is, you know, if you have a gas stove or gas heat in your home or whatever. But that kind of natural gas comes from wells. They mine it, they frack it out of the ground and so on. In the atmosphere, part of the increase in methane in recent years has been because, like, you know, the pipes that distribute natural gas are very leaky, as are the wells. But most of the increase is actually because two important sources of, well, actually several important sources of methane have been increasing. One is cattle, particularly cattle in high-density feed yards. There's no easy way around it. Cattle flatulence, cow farts. Cattle that are raised in high-density feed yards, they have a lot of gastric trouble, and they produce a lot of methane gas by farts, and this gets added to the Earth's atmosphere. It's an important source of methane. Another source of methane is termites. Termites are perfectly natural, but there are increasing numbers of termites in the Earth's in the ecosystem. It's beyond the scope of the class's wide number. Termites are increasing, but they produce methane as well. Also, rice paddies. You know, like where they grow rice in those flooded fields. They look beautiful, but rice paddies are actually environmentally a disaster, and the bacteria that live in rice paddies produce a lot of methane. So you can see again the amount of methane in the Earth's atmosphere has been increasing dramatically over the last 100 years or whatever it is. Alright, if we go back and start talking back to our original definition of what we meant by air. We said air is a mixture of these gases. They might be variable, they might be constituent gases, and aerosols. Let's time to talk about that word aerosols for a minute here. Aerosol are any kind of little particles of solid or liquid that are suspended in the Earth's atmosphere. This can be things like soot, smoke, dust, pollen, salt, etc. Things, little specks that are in the Earth's atmosphere. They're way too small to see. Okay? The air is full of this stuff. There are hundreds of thousands of them in every cubic centimeter of the Earth's atmosphere. And there's a few hundred of them in every cubic centimeter of the Earth's atmosphere that are surprisingly big. I mean, they're still too small to see with the naked eye, but they are big enough that they are involved in the processes, for example, as to how clouds get made and so on. But we'll learn all about that in a coming module of the course. Soot, smoke, pollen, dust. My guess is you don't have terrible difficulties figuring out where those kind of things would be coming from. Salt might be kind of a mysterious one for you. There's a lot of salt in the Earth's atmosphere. In fact, salt can be the biggest, in terms of how much of the aerosol there is, salt can be the biggest one. Salt comes from the ocean. When salt water, when there's a splash of a wave, it produces these little droplets of sea spray, and some of those sea spray droplets will evaporate before they hit back into the ocean. There's salt water, the water evaporates off, and it leaves behind a little crystal of salt in the atmosphere. Salt crystals are going to turn out to be very important for like the formation of raindrops and so on, but again, we'll get to that in a later module. Okay, finally today, one last topic in our first lecture in ATS 113 is about the origin of the Earth's atmosphere. Why do we have an atmosphere at all? Where did all this atmosphere come from? Well, it turns out the atmosphere that's around us right now is what we call Earth's second atmosphere. When Earth first formed 4 billion years ago out of a planetary nebula, or whatever the right word is from astronomy or whatever, an atmosphere formed with the Earth. As the different particles of dust and such that coalesced together to make the Earth form, there was also gases. Those gases were largely hydrogen and helium. Did you notice when we did our list of gases in the Earth's atmosphere, hydrogen and helium weren't in there? There's a reason for that. We lost those gases. Those gases are very light, and those gases, the molecules of them move very fast. Air molecules, as we're going to learn in this class, are actually moving very fast. The nitrogen molecules, the oxygen molecules, the water vapor molecules in the Earth's atmosphere are bouncing around in the Earth's atmosphere at about 1,000 miles per hour. But hydrogen and helium molecules on the Earth move even faster. In fact, they move fast enough that some of the molecules are actually of hydrogen and helium are actually moving faster than the escape velocity of the Earth. If you put an atmosphere on the Earth made of hydrogen and helium, some fraction of those molecules get away every day out into space just because they're moving faster than a rocket. They're moving faster than the escape velocity of the Earth. Those molecules leave the Earth's atmosphere and go off into interplanetary space, and they don't come back. So that first atmosphere that formed with the Earth like 4 billion years ago was lost over a course of a few hundred million years. All those hydrogen and helium molecules bled off into the Earth's into the interplanetary space, because sooner or later every molecule had a period of time where it was moving faster than the escape velocity of the Earth and headed off into interplanetary space. Our second atmosphere on the Earth, which is the one we're currently breathing now, primarily comes from a process we call volcanic outgassing. When you picture a volcano, I know you're thinking of like the explosions of lava and stuff like that, but that stuff's all bubbling out of there because of the gases that are escaping too. That process of gases that escape from volcanoes and also from like earthquake faults and things like that, seafloor spreading events and things like that, the gases that escape from there are what makes up our current atmosphere. Like, that is where nitrogen in particular, but also carbon dioxide, to a lesser extent water, most of the gases that are in the current atmosphere, the second atmosphere of the Earth, came from volcanic outgassing. Before we go farther than that though, I want to make something clear, because I know from other semesters sometimes there's confusion about this. I'm not trying to say that like the Earth is hollow and full of air. These gases that bubble out of, you know, at like a volcano are in the magma, in the same sort of way that like the bubbles are in the Pepsi before you open the bottle. Okay, they bubble out of the magma in the same way that the bubbles of carbon dioxide come out of the Pepsi once you open it up. Okay, I don't want you to get this sense that there's like big trapped pockets of air inside of the Earth or something like that. No, it's dissolved into the lava and the magma. You notice though on this list of gases that come from the list of gases that came from volcanic outgassing, one was missing, and that was clearly oxygen. Oxygen cannot come from volcanic outgassing. That is not a source of oxygen. Rather, oxygen only comes from photosynthesis. So life had to evolve on Earth before there would be any oxygen. In fact, it had to be plant life, which had chloroplasts, or I don't know, whatever you learned in high school biology as to how photosynthesis works. It wasn't until that happened that we started having oxygen in the Earth's atmosphere. Interestingly, oxygen was originally just a waste product of plants, and in fact it was very toxic stuff. The cells that were evolved at that time, because they had evolved in a planet that didn't have oxygen, didn't need to be evolved to protect themselves from oxygen. Oxygen is actually surprisingly toxic stuff. It tends to damage cell walls and stuff like that. Now, a few odd 100 million years later, we find ourselves, you know, all of our plants and animals and bodies and all this evolved to protect our cells from oxygen. In fact, not merely survive in an oxygen environment, but requires an oxygen environment. But that was not the case at first. In fact, it was one of the first great hurdles life on Earth had to overcome, was learning to live in an atmosphere full of oxygen, because it was originally toxic for the Earth's atmosphere. Okay, so now that gets us to the end of the first lecture. Now, the way this is going to work is I have some questions for you, and we're going to kind of do this like an interactive sort of way. I'll give you the question here, and if you scroll down a little bit in blue line, you're able to answer the question, and then depending on whether you got it right or you're wrong, you'll see a different video and we'll move through. I think I have about 4 questions to ask you. Alright, the first thing I want to ask about is, which of these processes here is a source of water vapor in the atmosphere? Is it the evaporation of raindrops? Is it the formation of a cloud? Is it the formation of dew on a grassy surface? Or is it the melting of snow? So think about those processes. Which one of them would be adding water vapor to the Earth's atmosphere? And make your choice and move on, and we'll see what happens.